The eddy current sensor can measure the distance between metal conductor and the probe surface statically and dynamically. It has the characteristics of non-contact operation, high linearity, and high distinguishability. It is a non-contact linearization metrology tool. The eddy current sensor can accurately measure relative displacement changes statically and dynamically between the metal conductor and the probe end face. In this lesson, we mainly study the eddy current effect and eddy current sensors. First, let's study the eddy current effect. Its principle is shown in the figure. A coil is wound around a square conductor and an alternating current is introduced. So the coil generates an alternating magnetic field. Because the conductor in the middle of the coil can be equivalent to a closed circuit in the circumferential direction. As the magnetic flux in the closed circuit is constantly changing, electromotive force and current are induced along the circumference of the conductor. The direction of the current will rotate along the circumferential direction of the conductor. It looks like a circle of vortex, so this phenomenon of electromagnetic induction and induced current in the whole conductor is called eddy current phenomenon. The longer the overall circumference of the conductor, the higher the frequency of the alternating magnetic field and the greater the eddy current. The eddy current inside the conductor also generates heat. If the resistivity of the conductor is small, the eddy current will be very strong and generate great heat. The eddy current effect is widely used, such as damping brakes in electric measuring instruments, eddy current brakes of high-speed locomotives, and induction cookers which utilize the eddy current thermal effect. Next, we learn about eddy current position sensors. The eddy current position sensor belongs to variable magnetoresistance sensors, which converts non-electric measured parameters such as displacement into inductance or impedance using the eddy current effect. These sensors have simple structure, small size, wide frequency response, high sensitivity, wide measurement linear range, strong anti-interference ability, and so on. Its most prominent characteristic is that being able to continuously measure displacement and thickness without contact. Therefore, it is widely used and has promising development. The eddy current position sensor is shown in the figure. The eddy current position sensor is a kind of eddy current sensor in which coils are used as sensitive elements. When alternating current is applied to the coil and it is close to the metal conductor, the magnetic field generated by the coil will be partially offset by the one generated by the eddy current of the conductor, which will change the inductance, impedance, and quality of the coil. This change is related to the physical dimension, conductivity, and permeability of the conductor, as well as the geometrical parameter of the coil, the frequency of current, and the distance between the coil and the measured conductor. If one of the above parameters is changed and the others remains unchanged, sensors for various purposes can be made, which can measure various physical quantities without contact with objects having conductive metal surfaces. The eddy current position sensor is made according to the principle of taking distance as a variable. After that, we will learn the working principle of eddy current position sensors. The structure and working principle of eddy current position sensors are shown in the figure. The sensor is mainly composed of probes and detection circuits. The probe is mainly composed of coil and skeleton, while the detection circuit is mainly composed of oscillator, wave detector, and amplifying circuit. When the high-frequency voltage generated by the oscillator is applied to the inductance coil L near the side of the metal plate, the high-frequency magnetic field generated by L acts on the surface of the metal plate. Because of skin effect, the high-frequency magnetic field cannot penetrate the metal plate with a certain thickness, but only acts on the thin layer on its surface, resulting in induced eddy current on the surface. The magnetic field produced by eddy current only acts on the coil L, which leads to the change of inductance and equivalent impedance of the sensor coil L. The functional expression of equivalent impedance C of sensor coil L affected by eddy current is shown in the figure. P is the resistivity of the measured conductor, mu is the permeability, R is the size factor between the coil and the measured conductor, W is the frequency of coil excitation voltage, and X is the distance between the coil and the measured conductor. When the measured object and the sensor probe are determined, some parameters affecting the impedance C of the sensor coil L are unchanged, and only the change of the distance between the coil and the measured conductor X is related to the impedance C. If the change of impedance C is detected, the displacement of the measured conductor can be detected. Finally, let's look into the applications of eddy current sensors. The eddy current sensor can measure the relative distance between the measured body, must be metal conductor, and the probe surface statically and dynamically without contact. It has characteristics of high linearity, distinguishability, reliability, sensitivity, strong anti-interference ability. It offers a fast response speed and its performance is not affected by the media, whether it be oil or water. Therefore, it is commonly used for analysis of axis displacement, shaft vibration, and bulging fork, descent ration, and other states of large high-speed rotating machinery such as steam turbine, water turbine, blower, compressor, and gearbox. In this lesson, we have learned about the eddy current effect and its applications. After class, you can refer to the applications of eddy current sensors in textbooks and understand the working principles of them. That's all for this lesson. Thank you.